So in this video, what we're going to do is we're going to look at the full adder circuit, which we've studied in the lecture note in lecture number 4, and we're going to basically show how a very simple circuit such as the full adder, which is really only composed of 5 gates, that we can actually demonstrate firstly that it will take care of our basic binary addition facts, which is the table that we can see on the left hand side of the screen. And then what we'll demonstrate is that not only can it do that, but if we aggregate full adders together to make larger circuits, that we can take care of addition of larger sums than just 0 and 1. We'll be able to add together, for example, 1, 1, 1, 1, which is decimal 15, to 1, 1, 1, 1, which is also 15, and we'll be able to get a sum. So what we'll be able to do is to show that very simple Boolean gates can be aggregated together to produce really very useful and powerful functionality. So what you should have to hand as you think about this video, and certainly if you want to try this yourself, and I strongly encourage you to do this, you need to have your lecture note, which is the lecture note number 4. Which you should have access to. You should have that from class, and in addition you should have Logisim running on your computer. And if you don't want to create the circuits from scratch yourself, although you can and perhaps you should, you'll find that the circuits are available in zip files on Blackboard. So I've provided 2 zip files. One is for lecture 2, which is just showing you the basic Boolean type gates, and then lecture number 4, there's a zip file for that, and that shows you all of the circuits that you can see in this in this video. So without further ado, we'll go ahead and we'll proceed through through the simulation of the full adder circuit. So what I want to do in this particular section of the video is to wire up a very basic full adder circuit. So we can do that in Logisim quite easily, basically by taking our gates and orientating them in the right direction and then wiring them up. So we need, for this particular gate, for this particular circuit, 2 AND gates like so, and we need also as well 2 OR gates, or exclusive OR gates, like so, and we then need an OR gate which faces south. So we can do all of that quite easily, and once we have them roughly arranged, what we can then do is wire them up to each other as per the schematic that you can see in the lecture note. And when we've done that, and we've also connected the input pins and the output pins, we can then test the circuit against the binary addition facts which are represented in the truth table. So I'll carry on wiring this up, and in a second we will test the circuit and we'll see how well it works. So at this point we've wired up the full adder circuit, and what we're going to do now is we're going to consider the behaviour of the full adder circuit in regard of the truth table that we can see in the lecture note. So really what the truth table does is it describes the 3 inputs and the expected outputs for particular combinations of inputs. So one way to think about it is that what we can do with this truth table is we can write it out in a slightly different fashion, which is what I'm going to do now. So the types of sum that we're doing are things like this. So for example, we might write 0 plus 0 plus 0 will give us an output of 0 with a carryout of 0, C out equal to 0. But we can also represent that like this. We could do it as 0 plus 0 with a carry in of 0, and that would of course give us 0 with a carry out of 0. So that doesn't seem particularly meaningful, but if I try something like this, where we write 1 plus 1 plus 1, well, that equals 3 in decimal, but if we write 3 as a binary string, we write it horizontally, we actually have 1, 1. So that's the 2 plus the 1, that gives us 3. So if we write that in a column fashion, well, that's 1 plus 1 plus a carry in of 1, and that will give us a sum of 1 and a carry out of 1, which goes into the next column. So we need that behaviour if we're going to be able to do sums like this. If, for example, I want to write 1, 1, 1, which is the binary representation for 15, and add 1 to it, well, obviously what I need is the ability to do column arithmetic. So the first column, which represents the ones column, 1 plus 1 will give us 0 with a carry of 1. Well, that's okay, we don't need the full adder circuit for that. But then if we look at the next column, which is 1 plus 1 plus 0, well, if I want to do that particular sum, which has 3 digits, A and B, and the carry in, which is up here, then I need to be able to have a circuit that can cope with 3 inputs, A and B, and then the carry in. So 1 plus 1 gives us 0, which is and a carry on or a carry out of 1, which then becomes a carry into the next column. The next column's addition, which is the 4's column, that's 1 plus 1 plus 0 gives us 0 with a carry of 1 to the next column. 1 plus 1 plus 0 is 0 with a carry of 1 to the next column. And although it's not shown, we could write in an additional 5th column of zeros, and that final addition would be 1 plus 0 plus 1, 1 plus 0 plus 0, which would be 1, and that is our completed sum. So that is, of course, 16. So we added 15 plus 1. Okay, and that would give us a decimal sum of 16, and that's the binary representation of it there. So really the problem we're trying to solve with the full adder is doing these 3-digit column additions. So if I go back here, you can see that the truth table tells us what the outputs will be for particular combinations of A and B and the carry in. So if A and B are 0 and the carry in is 0, then the expected output, the sum output, will be 0 and the carry out output will be 0. So we'll test that by going to Logisim, and you can see that if I put the circuit into simulation mode, the little hand icon appears, and I can set A to 0, B to 0, carry into 0, and then we can observe that the sum output and the carry out output are 0, just as we would expect. So if we then look at the second line of the truth table, you can see that A and B are set to 0 and the carry in is set to 1, so that would be 0 plus 0 plus a carry in of 1, which would give you a sum of 1 and an output of 0. So we'll do that. There's the circuit now set so that the carry in is 1, and you can see that the output as required is 1 in the sum and 0 on the carry out. If we look at the third row, B is set to 1, A is 0, and the carry in is 1. So again, if we provide that input to the circuit, we can see that the expected output, which is that the sum will be 1 and the carry out will be 0, that's exactly what we would expect to see, and that's what we do see on the behaviour of the circuit. There's the sum at 1 and there's the carry out at 0. Fourth row of the table, we're slightly different now. The sum is going to be A and B and the carry in, where A is 0, B is 1 and the carry in is 1. So that will give us an output of 2 if you want to express it in decimal, and that would be a sum of 0 and a carry out of 1. So I'll just write that out in the longhand for you so that you can see what that means. So the sum we're doing, if we go back to the truth table, is 0 plus 1 plus 1. So we'll write that in. So there's 0 plus 1 plus 1. And if we were writing that in decimal, we'd write down 2. But if we're writing it out in binary, well, 2 is 1, 0. Now you know that in column arithmetic, you're not allowed to have 2 digits. So 1 digit gets recorded, which is the first digit, which is the units part of the sum, the column sum. And then the second digit, which is the 2's digit, that gets pushed on to the next column. So if we write it like that, I think it's quite clear that this part represents 2. And then if we write it as a column sum, which is A set to 0, B set to 1, and the addition written like that. And then we have the carry in up at the top here, which is 1, like so. Then the sum becomes 1 plus 0 plus 1, gives us a sum of 1 and a carry of 1 into the next column. And that makes sense because if you think about this for a second, this column here is 2 to the power 0, which is equal to 1, the units column, and this column here is 2 to the power 1, which is equal to 2. And basically, if we're adding together values in this column and they sum to 2 or 3, then we have to record the new value into the next column. So we've got a sum here which is 2, the 0 stays in this column and the 1 goes into the next column where it represents the actual number value 2. So that makes perfect sense if you think about how binary numbers are actually structured. So that was line 4, and that then takes us into line 5, which is A set to 1. So again, if we go back to the circuit and set A set to 1, of course the expected output should be a sum of 1 and a carry out of 0, and that's exactly what we see in the circuit. Line 6 is A set to 1 and the carry in set to 1 with an expected output of 0 on the sum and 1 on the carry out output. And when we do that in the circuit, you can see that we get the expected output. There's the sum set to 0, there's the 1 on the carry out, exactly as we would expect. So that takes us to line 7, where A and B are 1 and the carry in is 0. So the sum output should be, when we set the inputs correctly, 1 in the carry out and 0 in the sum. So 1 and 1 gives us 2, and that's exactly what we're seeing in the outputs there. And then the final line in the truth table is where A and B and the carry in are all set to 1. So if we write that sum out explicitly, we could have something like this. So A is 1, B is 1, and the carry in is 1. So that gives us 3. And if we write that as a standard column sum like so, 1 plus 1 is obviously going to be 2, but if we set the carry into 1, it's now 1 plus 1 plus 1, which means that we have a sum of 1 and a carry out into the next column of 1. Okay, so remember that carry outs become carry ins. Carry out from one column is a carry in to the next column. You need to keep that point in mind for when we look at aggregations of full adders. But the conclusion that we can reach at this point in the video is that, I'm sorry, this is the last line here. So this is 1 for A, 1 for B, and the carry in is 1, and there's the sum output of 1, and there's the carry out output of 1. But the conclusion that we can reach is that if we're adding 2 digits, A and B, and we have a carry in, we can add together a range of numbers whose eventual sum is 0 through to 3. So that's not much use by itself, but we can see that it is principled enough that we could aggregate these guys together, aggregate full adders, and take care of arbitrary addition. And the idea of the principle that's being applied here is that you solve the problem for the simplest case, and once you've done that, you can then replicate for much larger and more complex instances of the same problem. And it's remarkably easy to do that in Logisim, and I'll show you that next. Okay, so we're looking at the full adder circuit that we created a moment ago. And what we're going to do with this circuit is we're going to package it up into a chip or a box or a package that we can then use as a component in larger circuits. So the principal difference between the circuit that we were using earlier on and the circuit that I've got in front of me is that each of the pins has been given a specific name. So for example, I'm clicked on pin A and you can see that I've labelled it A. Pin B has been labelled B, and the carry in pin has been labelled carry in. Now this isn't strictly speaking necessary, but we'll see later on that it's very helpful when we go and we package up this circuit. Okay, so what I've done also as well is I have clicked in the project menu and I've selected add circuit. When I do that, I get presented with a dialog, and the dialog allows me to specify the name of a circuit in addition to the main circuit. So just for the sake of illustration, I'll create a circuit which I'll call test FA, test full adder. I'll click OK, and then you can see that it appears down here at the bottom. And then what I'll do is I'll go back up to main, and I'll take my component, my circuit, my full adder circuit. I'll cut it out of the canvas that I've been working on, double click on test FA, and then paste that circuit in there. So you might say, well, what has that done? It doesn't appear to have done a great deal. The circuit isn't changed in any way. But if I go back to the main circuit and then click once on test full adder and drag it on to the canvas, you can see that the circuit that's represented there is presented as a box. So the question is, what is going on? Well, the box represents the full adder circuit, and inside that box the two AND gates, the two exclusive OR gates, the OR gate and the wiring that connected them are stored. But we can't see that anymore. So what we say is that the detail, the implementation detail of the full adder has been abstracted away or packaged away, so that now all we can see is the inputs for that particular circuit. So that allows us then, if we want, to wire up the inputs, and you can see that the inputs are labelled. That was the importance of labelling the pins that we talked about earlier on. And basically we can wire up our circuits to pins like so, and then we can connect them like this, and we can test the circuit. So I'm not going to do this in the full detail that we had when we looked at all 8 addition facts for the full adder circuit. But just to illustrate, I'm going to add together in simulation mode A and B set to 1 with a carry in of 1, and as expected you can see that the output pins provide us with 1 1, 1 in the sum, 1 in the carry out, and that of course represents the addition of 1 and 1 and 1, which is 3, or if you prefer in binary, which is 1 1. So the benefit of doing it like this is that we can hide the complexity of the full adder and treat it just as a component. So it allows us then to quite easily wire up a new circuit with full adders without having to specify every time we want to use a full adder the 5 gates and the individual bits of wiring that we'd need to work them out or to get them to wire together. So it reduces complexity and it lets us do more sophisticated circuits, and that's what we'll demonstrate next. But that's the mechanism that's available in Logisim for this, for doing this, and it's an immensely powerful mechanism because it allows us to, as I said, to solve a problem in its simplest possible dimensions, and to then extend that solution quite easily to much more complex and larger problems, and we'll demonstrate that next. So we've so far looked at simple addition. What I want to do is to imagine a situation where we're adding together decimal 7 plus 2. So obviously if we do that addition, it gives us decimal 9. So if we write that out as a binary number, decimal 7 becomes in binary 0, 1, 1, 1, and decimal 2 becomes in binary 0, 1, 0. Okay, now this is what I would describe as a 4-bit addition, in the sense that the A word, which is this guy here, and the B word are both 4 digits in width. Now you might say, well, hold on, you would never really write a sum like that, because this 0 here is not significant in terms of the overall value of the number, nor are these zeros here. But the reason why we do it like that is that the computer adds all the columns of numbers that it's presented with, and it always deals with numbers in a fixed width package. So even if you are adding together 1 plus 1 inside the computer, if we were using 8-bit representations of binary numbers, then the binary number 1 would still have 8 digits. It would have 7 zeros, which would represent the non-significant numbers, and if we were adding 1 and 1 inside a computer whose representation of binary numbers was 8 bits in width, well, the sum would look like this. It would be 1 plus 1 would give you 0, carry the 1, and then 1 plus 0 plus 0 would be 1, and then the carry out of that, which would be 0, and keep in mind that that would be accounted for in the truth table, would be 0 plus 0 plus 0, with a carry out of 0, 0 plus 0 plus 0, with a carry out of 0, 0 plus 0 plus 0 gives us a sum of 0, with a carry out of 0, 0 plus 0 plus 0 gives us a sum of 0 with a carry out of 0, 0 plus 0 plus 0 gives us 0 with a carry out of 0, 0 plus 0 plus 0 gives us 0 with a carry out of 0 to the next column. So even though the two significant digits that are actually getting added here are the two digits at the very beginning of the first word and the second word, the actual computer will actually add together the remaining 7 columns, even though the addition in 6 of those columns is not meaningful, because you're just adding 0 and 0 and 0 to get a sum of 0 and a carry out of 0. But the circuitry is constructed, as we'll see in a minute, in such a fashion that that's the way that it is done. That's the way that it has to be done inside the computer. So just to go back to this sum here, if we were to do this as a pen and paper exercise, we would see that the first column would be 1 plus 0 to give us 1, with a carry out of 0 to the next column. 0 and 1 and 1 would give us 0 with a carry out of 1 to the next column. 1 and 1 and 1 would give us, and 0 would give us 0 with a carry out of 1 to the next column. And then finally we'd have 1 and 0, which would give us 1 on the sum and a carry out of 0 to the next column. Now when we look at the resulting sum, that is 8 and 1, that gives us 9, so that is the correct result. Now you can see that previously we took our full adder circuit, which looks like this, and we packaged it up so that we could present it into another circuit as a plain simple box, and that the only thing that we would see would be the inputs to each full adder and the outputs, which would be the sum and the carry out. So what I've gotten set up in Logisim at the moment is a 4-bit adder. And what a 4-bit adder does is it takes two inputs, which are the A word and the B word. It also takes a carry in for the first column. And the basic idea is that each digit of the A word is added to the corresponding digit of the B word. So A0 is added to B0, A1 is added to B1, A2 is added to B2, and A3 is added to B3. So you can see that there is a full adder for each of the columns of this 4-bit sum. So the first full adder that the mouse is over at the moment, that takes care of the ones column, which is A0 and B0. The second full adder takes care of the twos column, which is A1 and B1. The third full adder takes care of the fours column, which is A2 added to B2. And finally, the fourth full adder takes care of the eights column, which is A3 plus B3. So the idea is that we have input pins up here, which represent the two 4-bit numbers that are to be added together, the A word and the B word. And we have a carry in for the first column, which will always, in the examples that we'll be doing in the next minute or so, be set to 0. And then what we'll be able to see is the outputs presented down here on these output pins, and they'll represent the sum, the overall aggregate sum of the A word plus the B word. So what I'm going to start off with, first of all, is the simplest possible sum, which is setting the first digit of A to 1, and we'll leave B set to 4 zeros. So effectively what we're doing is we're adding together this sum, which is A 0, 0, 0, 1 plus B, which is 0, 0, 0. And when we do that, we get 1 plus 0 will give us 1 with a carry of 0, a carry out of 0, which becomes the carry in to the second column, the twos column, and that addition is 0 plus 0 plus 0, which gives us a sum of 0, and a carry out of 0, which becomes a carry in of 0 to the next column, the fours column, and that addition is 0 plus 0 plus 0, which is a sum of 0, and a carry out of 0 into the next column, which is the eights column, and that is a sum of 0 plus 0 plus 0, which gives us then a carry out of 0, which goes into the next column if there was an adder to take care of that, but which in our 4-bit circuit, as we'll see in a second, will output as 0 on the fifth output pin. Okay, so that's how it works in the pen and paper form. I'm just drawing in little arrows to show the key point, which is that carry out from one column becomes the carry in to the next column. So carry outs lead or become carry ins. My handwriting is deplorable, but you get the idea, and you'll keep that in mind when we go back to the circuit. So if I look at the first full adder, you can see that A0 is set to 1, B0 is set to 0, and if we look at the inputs, you can see that the input into the first full adder is 1, and you can see that the B0 input is 0, and that the sum output is 1, which goes to the first of the output pins, and that the carry out is 0. But if you look at the way that the circuit's wired up, you'll see that the carry out of the first full adder is wired up to the carry in of the second adder. So remember that the first full adder takes care of adding the digits that are in the ones column. The second full adder takes care of adding the digits that are in the twos column. The third full adder takes care of the addition of the digits which are in the fours column, and the fourth full adder takes care of adding the digits which are in the 8's column. If we made this circuit bigger and we had a 5th and a 6th full adder, then they respectively would take care of adding the digits that were in the 16's column and then the digits that were in the 32 column. And that could go on as for as many columns as we want, so long as we provide a full adder circuit to take care of the addition in that particular column. So that seems fine. If we look at the inputs to the circuit, A is set to 1, B is set to 0, and the output, which is what you would expect if A and B are 1 and 0, is a sum of 1. And you can see that there at the bottom of the circuit. So I'll set A back to 0, and we'll try a different sum, which is A, as before, set to 1, like so. And we'll set B equal to 1. So obviously when we do that sum, we'll get 1 and 1 gives us 0 with a carry of 1 onto the next column, and then 1 plus 0 plus 0 is 1 with a carry of 0 onto the next column. 0 and 0 and 0 is 0 with a carry of 0 onto the next column, and then finally we do 0 and 0 and 0, and that gives us a sum of 0 with a carry out of 0 onto the next column. So 1 and 1 gives us 2. That's what we can see there in that particular sum. And if I go back to my circuit, you'll see that when I set A0 to 1 and B0 to 1, we can observe a different behaviour. First of all, if I draw your attention down to the bottom of the circuit, you can see that the output pins are showing 0, 0, 0, 1, 0, which is of course the binary string representation of 2. And you can see as well that when we look at the first full adder, that its behaviour is that its sum output is 0 and its carry out output is 1. So a way of thinking about that is that the carry out of the first column of addition, where we added 1 and 1, is going to be 1 into the next column. So that's the, when we look at this second full adder here, what we're specifically looking at is this column of addition here, the 2's column. Okay, so the 2's column is the second column. So you can see that the carry in, which is this guy here, C in, yeah, is 1. You can see that A is 0 and B is also 0. And if we go and examine the circuit, there's A and B both set to 0, and there's the carry in, which is the carry out from the previous column addition, that's set to 1. So you can see that there's really quite a clear mapping between the purpose of each full adder and the actual pen and paper representation of the sum that we can do on paper. So you can see the relationship between the full adders and the actual columns of addition. Okay, so we'll do another sum. I'll set these guys back to 1, and we'll do a slightly larger sum, which will be 15 plus 7. Okay, so the behaviour that we'll see on this occasion will be slightly different, because we're going to have columns where the addition will be 1 plus 1 plus 1. So the first column is 1 and 1. So remember that we have that as the A word, that is the B word, and of course the first column also has a carry in, but that's always set to 0, at least when we're considering basic addition operations. And then if we actually perform the addition as a pen and paper exercise, we have 1 and 1 gives us 0 with a carry of 1 onto the next column. 1 plus 1 plus 1 gives us 1 with a carry of 1 onto the next column. 1 and 1 and 1 gives us 1 with a carry of 1 onto the next column. And then 1 and 1 and 0 gives us 0 with a carry of 1 onto the next column, and that then gets recorded directly down below. So we can see that 15 plus 7 is going to be 22. We can just verify that, so we'll just check that manually. So this one here represents 2 plus 4, that would be 8, and this is 16. So 16 plus 4 is 20, plus 2 is 22. Okay, so remember the sum was 15 plus 7, so that is the correct output. That's the binary representation of 22, which is what we see there. Okay, so let's go back to our circuit. We're still in simulation mode. So we set the A word to represent 15, so that's 4 ones like so. And you can see that the circuit immediately updates. As soon as I change the value of any of the pins, you can see that we get the circuit immediately doing the sum. So the sum of A when it's set to 1, 1, 1, 1, and B when it's set to all zeros is obviously going to be just A itself, which is shown at the bottom of the circuit, and that's 1, 1, 1, 1, 15. So we're going to set B now to 7, and when we do that, we can see that the circuit updates, and if we examine the output at the bottom, you can see that we've got 1, 0, 1, 1, 0, which is the same as our pen and paper output, and that is showing the correct binary representation of the sum of the A word and the B word, which is 22. So just for the sake of completeness, I'll do a final sum, which is going to be the maximum possible sum that we can carry out with a 4-bit adder circuit. So obviously if the A word can only be 4 digits, then the largest number that we can represent is 1111. So if we set the A word to 1 and we set the B word to, the A word to 4 ones, which represents 15, and we set the B word also to 111, well, there's no larger value that we can give to A or B. That's the maximum that we can set those two 4-bit numbers to. So if we go ahead and add them, then we'll end up with a sum. So remember, this is 15 and 15, so that should give us a binary number or a binary output which represents decimal 30. So we'll check that. 1 plus 1 is 0, which a carry out of 1, which becomes a carry into the next column. 1 plus 1 plus 1 is 1, with a carry out of 1, which becomes a carry into the next column. 1 plus 1 plus 1 gives us 1, with a carry out of 1, which becomes a carry into the next column, and that gives us finally 1 plus 1 plus 1, which is 1, which gives us a carry out of 1, which then gets recorded just directly below. Okay, so to verify that that is 32, we'll just look at the individual digits and we'll say, okay, that's 2, 4, 8 and 16. So 16 plus 8 is 24, plus another 4 is 28, plus 2, that gives us 32. So that is the correct, sorry, what did I say there? 16 plus 8 is 24, plus 4 is 28, plus 2, it's not 32, of course it is 30. And you can see that we need 5 digits to represent that. But that's the maximum sum that we can do with a restriction of 4 bits per word in terms of the input. So we'll set that up now, and if we look at the outputs, you can see that the sum update, the sum has now been updated to 11110, and that's the same as our pen and paper exercise, like so. So just to very briefly recap on what we're doing there, we have implemented a full adder circuit, we've packaged it up, and then we've wired 4 instances of our abstracted full adder circuit together to create a 4-bit adder, and we've demonstrated that that 4-bit adder can carry out additions on 4-bit input words A and B, and we can now do a range of sums from 0 through to 30. So we're making progress. The minimum requirement of a computer, you would think, is that when it computes, it can at least do some addition. And we've gone from adding 1 digit to 4 digits, and we've increased the capacity of our computer quite considerably. But it's still not good enough, and that's what we'll look at next. Okay, so we can take our 4-bit adder and we can package it up as a component that Logisim can access. So you can see that I've done that in Logisim. Previously we did it for packaging up just the basic full adder circuit into a full adder component, but now I can do the same thing with the 4-bit adder that we were looking at just a moment ago, and I can bring it in to an empty circuit and then wire it up. So that's exactly what I've done. You can see that I've packaged up the circuit and I can now connect an A word which has 8 bits and a B word which has 8 bits to 2 4-bit adders. So you can see the complexity of this is just getting a little bit more complex in terms of the wiring, and you can see that obviously we're doubling the capacity of our circuit to do additions. But this circuit is essentially the same as the 4-bit adder, and in fact we'll see in a second that we can make a 16-bit adder, we can make a 32-bit adder, and so on and so forth. But the behaviour of this circuit is exactly what we would expect. So if I switch this to simulation mode and I set the A word to 1, well, we're adding 1 to a B word of 0. You can see that the pins for B are set all to 0, and you can see that the sum output is 1. So 1 plus 0 would give us a sum of 1. If I set B0 to 1, you can see that we're now adding 2 8-bit words which represent respectively decimal 1 and decimal 1, and the output is S1. That's equal, if you like, to 1 0, which is of course the binary representation of 2. So we'll set A1 to 1, so that means that the A word now represents decimal 3 plus the 1, well, that would be 4, and right enough, if we look at the sum outputs here, you can see that that is 1 0 0. That's the binary representation of 4. And so it goes. If I make all of the A pins 1, well, that will be equal to decimal 255. That's the largest decimal that you can represent with 8 bits. And if I set B to 0, then obviously the output pins will just be 8 ones representing the binary representation of decimal 255. But then if I set B to 0, we'll be adding 1 to that, and we'll get an output which is 256. And in fact, if you look, you can see the 9th pin, which is the carry out of the B adder, carry out of the last full adder gate, that goes high. So if we just think about that for a second, and I'll do that maybe as a pen and paper exercise. So here's the A word, which we represented just a second ago. So that's 1 1 1 1 1 1 1 1 plus B, which is 0 0 0 0 0 0 0 1. So this guy here represents 255, and this guy represents 1. So if we add that together, that would be 256, okay, which also happens to be 2 to the power 8, okay, which is the 9th column, or the 9th digit. But let's go ahead and do the addition. I'm going to fly through this because we're getting into larger numbers. I don't think I should laboriously go through each column, but 1 plus 1 gives us 0, carry the 1. 1 plus 1 gives us 0, carry the 1. 1 plus 1 plus 0 gives us 0, carry the 1. 1 plus 1 plus 0 gives us 0, carry the 1. 1 plus 1 plus 0 gives us 0, carry the 1. 1 plus 1 plus 0 gives us 0, carry the 1. 1 plus 1 plus 0 gives us 0, carry the 1. 1 plus 1 plus 0 gives us 0, carry the 1. And here we are in the 9th column. So all of the additions that were done up to this point were taken care of by the full adder. And this 1 that we're looking at here, this is just the output of the carry out of the last full adder. Okay, so we don't really do any further additions with it. It just gets directly output to the output pin, and that one gets dropped down in our pen and paper exercise like that. And of course, if we look at that, we can see that that is 256. It's the same output as we would see with the circuit that we've simulated. So we can go further with this. So you can see that I've also simulated a 16-bit circuit. So the capacity of this is based on joining together two adders. So again, this seems to be quite more complex, but it's not really. It's the same principle as before. You've got an A input and a B input, and instead of having 4 or 8 digits of binary input, we now have 16. Okay, so that's 2 bytes each. We have a sum output, which is also 16, and we have a pin for representing the carry out. You can see that I took the previous circuit, our 8-bit circuit, which was made out of 2 4-bit adders, and I've aggregated them together so that now we have an 8-bit adder, and I've wired them together using a special type of circuit component which is available in Logisim, which is called a splitter. So the splitter allows you to use circuits, to use wires which can transfer in parallel 8 bits or 16 bits or whatever it is that you want in terms of width. So it tidies up the circuit a little bit and means that the wiring is not desperately complicated. So I'm in simulation mode. I'll set A to 1 as we did before, and you can see that if we find the outputs over here, there's A and B, where B is 0 and A is 1. Well, the output of that addition is 1. And if I set B to 1, like so, you'll see that the output of the circuit is 2. There it is there, 1, 0. And basically we can do binary operations, so that's 15 for the A word plus B set to 1, and if we look at the output, it is 16. So I'll leave it to you to experiment with that. Okay, so we can take this to the logical conclusion, and we can set up a circuit where there are two 16-bit full adders. And you can see that I've done this. It's the same principle as when we were wiring together the 16-bit adders. So we take our two components, we connect them together. The A word gets connected to the A inputs of the two full adders. The B word gets connected to the two B inputs of the full adders, and then we have our carry out and our sum outputs being sent to the corresponding pins. So all of this is made possible because Logisim will let you specify that the input pins have a particular width. So for example, if I click on the A pin and I go and look at the attributes of that, you can see that the number of data bits that it allows as inputs are 32. The same for the B input and the same for the sum output. So if I set this to simulation and I reset the simulation so all the registers are cleared, and I set the A word to whatever value I want, so it's quite a large sum value, and then I randomly click inside the B word. Well, I'm not going to check this, but I can be confident that this is the correct sum output. And then the final thing is to show the final package, which is a 32-bit full adder circuit. It's a ripple parallel adder circuit, and you can see that all of the complexity. And keep in mind that inside this box, if we could explode it and look inside it, what would we find? We'd find 32 full adder circuits. Multiply that by the number of gates, so that would be about 160 individual gates wired together. But all of that complexity is hidden by Logisim. We've abstracted it away until we end up with a very simple box that is able to do really quite impressive addition. So if we've been following this carefully from the very beginning, what we can basically say is that in our description in the lecture notes, we've shown how transistors can be wired together to provide us with basic Boolean functionality, and that would be our NOR, our NAND, our AND, or, not, exclusive or, exclusive negated or gates, which when we look at them initially don't seem to have any particular utility. But if we wire them together into circuits like the full adder, we can see that that provides us with a very basic set of binary addition facts, and then we can take that full adder circuit and aggregate it together to create larger circuits such that we can do addition on arbitrarily sized inputs. So Logisim, the maximum size of a circuit that we can specify is 32 bits, but inside real computers, the adder circuits would be able to cope with 64 bits, 128 bits, maybe even 256 bits. So at that type of width of inputs inside a computer, you're adding together very, very large numbers indeed. And what we'll see is that with addition, which is the fundamental operation of arithmetic, once we have that particular problem solved, then we can do subtraction, which is what we'll look at next in the next video and in the next lecture. But also we can then do things like multiplication and division, which are nothing more than repetitive addition and repetitive subtraction. So for the price of one circuit, we have, from one very simple circuit, we have actually managed to solve 4 fundamental operations of arithmetic, and we've demonstrated that by using Logisim.